take a clear and still photo of this hummingbird, the shutter speed of a camera must be less than the characteristic time taken for it to flap its wing once. Otherwise, we'd get a blurry image. To photograph smaller and faster things, like atoms, methods such as pump probe spectroscopy use laser pulses with width shorter than the characteristic time for atomic motion. To photograph even smaller things like electrons, the characteristic time involved is an attosecond, which is a billionth of a second. To produce such short duration pulses, we use a tool called Fourier analysis. Here we add together lots of sine waves of the same amplitude and increment the frequency linearly. We also adjust the phase of the waves. A phase of a wave is just a leftward or rightward shift. When the laser produces all these waves at the same time, constructive and destructive interference occurs at various locations to give us pulses of short width. In order to photograph even faster things like electrons, the laser source needs to superpose even more high-frequency sine waves. This is not possible to do directly. One of the research works of Nobel laureate Anne Louis featured passing intense infrared laser through noble gases like neon, leading to higher harmonic generation, or HHG for short. To understand the mechanism of HHG, consider the electron of a neon atom trapped inside a potential well, which shows the associated energy at different locations. The electron is depicted as a probability wave, indicating the likelihood of finding it at a location. The laser light, which is oscillations of electric and magnetic fields in space, can cause the steep walls of the well to become less steep, providing the electron wave enough energy to spill out. The electron is said to tunnel out of the well. Then, when the electric field reverses direction, the electron, now pictured as a particle, re-enters the atom via emitting those extra energy as high-frequency waves known as high harmonics. In order to visualize these high harmonics, pluck a low E on a guitar string. As you can see, there are peaks at frequencies twice, thrice, or quadruple the fundamental frequency. These are known as the overtones or higher order harmonics. Anne Louis' experiment showed that there exist odd overtones from around 5th to 33rd where the intensities are roughly equal, forming a plateau region. And since these overtones naturally have linearly increasing frequencies, they satisfy the condition to form pulses. Et voila, combining these, we have our attosecond pulses of light. So, why do we care about attosecond pulses of light? With emerging new applications, this just might be the next major breakthrough.